All right, good evening, or you could be watching this at the time of the class. This is a replacement for Friday's class. We're going to have a couple of shorter videos. We'll see how much shorter because they are going to add up to be about like a class is. Because we are covering this in lieu of having class together. But we have had a good discussion of the foundation of this, the idea of how do you describe what electrons do in words, and now we're applying that more and more to specific situations. In fact, one specific situation is how drugs work, how drug companies make money. And once I was at a party, and as you do, you meet a biochemist and you start talking to them. And I was actually kind of curious. I was like, I'm teaching my students Michaelis Menten kinetics, and I'm sure that you use something that's like way beyond that now, like this is like elementary school for you or things like that. No, he was like, no, actually, this is basically what I do. It's the foundation of everything we do, and I'm really glad that you're teaching it to the students. So, based on his words, we've got to learn it. We've got to keep looking at this and see what's going on. The reason that drugs come up in this topic is because drugs are something, one class of drugs will block enzyme function. So enzyme inhibition will be something that looks almost like a substrate, and it can do the first step of catalysis, but it can't do the second. Remember, the first step is substrate binding. The second step is catalysis, and those involve different parts of the enzyme. We even showed you with chymotrypsin how you had the binding pocket for the little phenylalanine over here, and then you have the amino acids that actually cause the amide to break over there. And we have that at the very beginning of the lecture about this. So the whole idea is that binding is not catalysis, and they actually take place with different parts of the protein. Because of that, you can have something that binds as well or better than the real substrate, and yet it doesn't have, for example, the amide bond that the chymotrypsin cleaves. If it doesn't have that, then you have the substrate sitting there, the substrate's trying to get in to be catalyzed, but it can't because there's an inhibitor already in the place. That's called a competitive inhibitor, and that is one way to block enzyme function. You have a molecule that looks like the substrate but is missing a piece. It's missing the catalytic piece, so it can bind, but it can't go on to product. There's another way to do it too. If you think about it, you can use the regular shape of the binding site and occupy the regular shape and just have a part missing. But what if enzymes are big and flexible? What if there's something that binds on the side, kind of like BPG and hemoglobin? Something that binds along the side and changes the shape of the rest of the enzyme, and it changes the shape of the binding site so that the substrate doesn't bind anymore. This is a more indirect method, but this would be a non-competitive inhibitor, something that changes the shape of the enzyme binding site. The cool thing about this is these will affect Vmax and Km differently, and they will look differently on a hyperbola plot, although that's hard to see. They will look differently on a Lineweaver-Burke plot, and that is what's easier to see. And that's basically our final topic of this chapter. Before we move on to chapter 11.3, but enough, we'll talk about that later. So from this explanation, you can see competitive inhibitors are going to have to look a little bit like the substrate. In fact, they have to look enough like the substrate to bind in its place. But they should have a part that's different. The part that's different is the part that participates in catalysis. So for example, here's methotrexate. I don't know if you've heard methotrexate. Usually there's a couple students who raise their hands. It is a drug that's used as chemotherapy against cancer, and it kills cells that make more cells. Cancer cells depend on that. The way that it does that is it binds into the binding site of tetrahydrofolate, which is a cofactor you're going to learn about in Biochem 2. Tetrahydrofolate looks like this thing on the bottom. That's the cofactor. Methotrexate looks like the thing on the top, and they look a lot alike. You can see how the enzyme would be able to bind both of them. But look for the differences. The differences are where the catalysis is going to take place. It turns out that methotrexate just has an ordinary little methyl group on that nitrogen there, that amine in sort of the middle. I think you can see my little pointer right there. But look down at tetrahydrofolate. There's a bunch of weird nitrogens, but there's no carbon attached there. That's because tetrahydrofolate is a little claw for carbons. It claws the two nitrogens bind a single carbon and it moves them around so you can build other molecules out of it. If the methotrexate gets in there, it can't let go of the little methyl group that it has, and so it gets in the way of the real tetrahydrofolate. That's why it kills cancer cells. Cancer cells need folate to build new molecules. Methotrexate blocks that. And in fact, we have right here a dihydrofolate reductase, which binds tetrafolate. You can tell that from its name. You can also tell it reduces it. At the same site, it binds methotrexate. So in fact, right here, we use this as an example, and it turns out that the thing on the right is an NADP type molecule. The thing on the left is our cofactor, and it's actually our competitive inhibitor will bind in that same place. You can even sort of imagine how this will bind into that cleft, because there's so many things that are the same. You just bind these charges on this side, you bind those nitrogens on that other side, and you end up saying that those are important for binding. So you can see that the inhibitor has the black parts are important for binding, the red parts are important for catalysis. What's the same versus what's different? And so methotrexate is used as chemotherapy because dihydrofolate is actually involved in building both purines and pyrimidines. I believe it's involved in adding the methyl group that makes uracil. Or it turns uracil into thymine. I think that might be it. Yes, I believe that's it. So anyways, don't trust me on this stuff. You'd have to look up the actual pathways. But I know that it's used for that somewhere. And because of that, cancer cells need lots of DNA to keep dividing. They need lots of dihydrofolate reductase to supply the carbons to help make the DNA bases. Methotrexate will block this. It will prevent the biosynthesis of the nucleic acids. Without nucleic acids, you don't have DNA, you don't have cell division, you have dead cells. But you see how this works. This will work for any dividing cell. It's just that cancer cells happen to be dividing all the time, whereas other cells will be quiescent for a short time. But this will have bad side effects on regular cells because it's going after something that every cell needs. Now there's actually, the thing about methotrexate, it's actually very effective against choriocarcinoma, which is a placental cancer. And actually what it is actually involves a, let me read you about it to make sure it's right. So one of the first doctors to try it, this is in the Emperor of All Maladies book, noticed that smaller doses weren't working, and so he upped the dose dramatically, and then it suddenly worked. Competitive inhibitors typically involve huge doses, and we'll show that in the data in just a second. So there's a doctor in Haiti that actually I'm related to, who treated an 18-year-old woman with choriocarcinoma, and she had bleeding, anemia, early metastasis to the lungs, and she's diagnosed with a pregnancy test because a choriocarcinoma is kind of like a tumor in the place of a baby. And what it does is the same hormones are produced by the tumor being implanted, but it's not a baby, it's a tumor. And so you actually have to, one of the ways you can diagnose it is you can diagnose it with a pregnancy test. So he could diagnose it even in Haiti with limited resources. And so he had a last minute request. And it's funny, at just that time, a church contacted him and said, we were just sort of praying about it and we sort of felt like we should give you something. Do you need anything? And he's like, yeah, I need some methotrexate because I have a patient who's going to die without it. They actually bought the methotrexate in the States. They actually flew someone on a plane with it. This is back in the day where you needed to do that if you really had an urgent need like this. And they actually brought the methotrexate. The woman was given it. She went from coughing up blood to walking out of the hospital in one day. Methotrexate is very effective against these placental choriocarcinomas. He saw it with his own eyes. So methotrexate works because in her body it blocked all the DNA synthesis. So how does that work, and how does that fit into the kinds of data that we were talking about? Well, it's a competitive inhibitor. Because of that, we can actually put it into our three-step enzyme mechanism. You see this on top. We've been talking about this all the time. We say we can model a Michaelis-Menten normal enzyme with these three arrows, two back and forth for substrate binding and one onto product. If a competitive inhibitor is working, it's going to be blocking one of these arrows, and the question is how. The competitive inhibitor binds free enzyme and prevents it from binding substrate. Therefore, we add two arrows for it. The inhibitor binds it, brings it to EI, and the EI cannot do anything else. The EI is blocked. We can show it with a scheme like on the left. We can show it with a scheme like on the right. Both of these schemes show competitive inhibition. And you know from the way that we worked out Michaelis-Menten kinetics from just the three arrows on the top that we can actually do a similar kind of thing with just adding in the new arrows we have on the bottom, the EI arrows. And what's really helpful, so this does change the hyperbola, but again, hyperbolas are hard to look at. Where it really matters is where it changes the Lineweaver-Burke plot, because this is so simple we can look at it and we can clearly see where the differences are. Basically, we run the Lineweaver-Burke, we collect all the data, we collect 6 or 7 hyperbolas, we draw a line between them, and we have, from the slope, we have the Km and Vmax, and from the intercept, we have the Vmax. All of that was covered in the last lecture. What we do when we had an inhibitor is we slow down part of the enzyme, but not necessarily all of the enzyme, and the parts that we slow down are important. If you look at this, remember it's a double reciprocal plot, so that means 1 over x is what we're dealing with. As we go up on the axis, we are actually going down in substrate concentration on the one hand, and down in rate as we go up on the y-axis. That means if we have an inhibitor that inhibits, it's going to move the line up. As we add inhibitor, so like without inhibitor, we call that alpha equals 1. It's like the whole plot is being multiplied by 1. And as we add inhibitor, the slope increases by a certain factor. When the slope doubles, we call that alpha equals 2. Then the slope triples, alpha equals 3. So each of these has an inhibitor concentration associated with it, and the alpha is just a factor for how much the slope changes. It's shown exactly up here in this equation, where you have the alpha on the Km over Vmax, which is the slope. If alpha equals 2, that means the slope has doubled when you've added that much inhibitor. What's really cool about this is that the alpha actually has an equation that relates it directly to Ki. Alpha equals 1 plus I over Ki. And that's how you can get the Ki from a plot exactly like this. But notice what's going on with this plot. What's changing when you add inhibitor? It's going up, but it's not all going up equally. The line is going up at the far right side of it. At the y-intercept, it's not going up at all. And remember that the y-intercept is exactly defined as 1 over Vmax. So what you have is you have a situation where the slope increases, the Km over Vmax increases, but the 1 over Vmax does not. Therefore, the only thing that's being changed is the Km, the Vmax is not being changed by competitive inhibition. You can test a drug, get the plot that looks like this on a double reciprocal plot, and you can say, oh, it's a competitive inhibitor. So I know that I've got to use large doses. I know that it works a certain way. It's not going to stick on there permanently. There's a lot of things you can know from it. This is pharmacology right here. And you can find out how tightly the inhibitor binds from alpha, because alpha is related to the equilibrium constant that makes the enzyme inhibitor complex. This is very cool, and this is how they would get the KIs in real life that they talk about in the paper. The way they actually do it in the paper is slightly different, but it's similar enough to this that this definitely prepares you for it. So the pivot point. Notice the pivot point is the y-intercept, and that's defined as 1 over Vmax. So if the pivot point isn't changing, that means the Vmax is not changing. The maximum velocity when you add infinite substrate is not changed because the infinite substrate will crowd out the competitive inhibitor. And so this is one thing that you can just know about competitive inhibition. It changes the apparent Km, but does not change the Vmax. And in fact, methanol poisoning is another example. Now remember, methanol is not ethanol. It's got 1 carbon shorter, and it's actually much more toxic to you than ethanol. Ethanol is a little toxic as it is, but methanol is actually super toxic, and you ever wonder why? Well, your liver doesn't like the toxin that you're feeding it, and so what it does is it brings out a dehydrogenase. It has an enzyme that will dehydrogenate alcohols. Dehydrogenase means you're taking away hydrogens and leaving behind a double bond. So if you're converting methanol to a double bond, think about that. Here's methanol on the left, and on the right you have the double bond, the dehydrogenated form, where you have a double bond. Anybody know what that molecule is? If you look at this is another way to look at the molecule. It's formaldehyde. Basically, if you drink methanol, you're basically drinking formaldehyde. Your liver's going to turn it into formaldehyde. And formaldehyde is a poison because it's a powerful cross-linker. It's got kind of two aldehydes on either side. It's not exactly like that, but you can see that it doesn't look right, and it's an unbalanced reactive molecule, and it'll actually cross-link proteins. That means it will turn them into gels, and it will make them stay in place, which is good for preserving samples, but not very good for living. So the thing that happens when you drink methanol and you basically convert it to formaldehyde first goes to the eyes. Blindness will result because light sensing ability is one of the most sensitive and nearly overloaded nerves in the whole brain. And so the freezing of the proteins is actually going to affect the most sensitive tissues first. And the optic nerve is a very sensitive tissue. This is why methanol poisoning will cause blindness. So, you're a doctor. Somebody comes in who just drank a bottle of methanol. They didn't realize that methanol is much worse than ethanol. Maybe they were wanting to get a little high or drunk or something, but it's not a good idea because you don't want to drink formaldehyde, and that's basically what you're doing. So what do? Competitive inhibition with another substrate. What's a substrate that's safe enough to give the patient that will also go into alcohol dehydrogenase? Well, you guessed it, ethanol. Now you don't actually act like you don't actually give it to them to drink. It's much more efficient to give it to them intravenously. But this is actually what you do. It's one way to treat methanol ingestion. You outcompete the methanol for the alcohol dehydrogenase, and you flood the system with high amounts of ethanol so the methanol stops reacting. Ethanol will compete with methanol, and the only problem is ethanol technically is not a classical inhibitor. It's used up because it's also a substrate. You have to keep on giving it to them to keep outcompeting the methanol until the methanol is cleared from the system. Okay, and that is the most common kind of inhibition. The slope changes and the y-axis, the y-intercept does not. Also remember that its E plus I was all the way on the left. When we have the E plus I all the way on the left, we had a Ki for it. Okay, that makes sense. So there's actually another kind where the E plus I is not from the free E, but it's right here in the middle from the ES. This is the same three-arrow process on the top. We're just adding the equilibrium of inhibitor binding in the middle. You have ES plus I going to ESI. It's pulled down here, and what happens is the ESI is now an inactive complex. And the way that can work is if substrate binds and it opens up a little binding pocket that then an inhibitor can bind to, and that blocks it from going on to product. It's a little bit weird to think about, but it can happen, and it's easier to think about if you just think about, well, before we had E plus I on the left, what if we had ES plus I? And it turns out that you can. That's uncompetitive inhibition. It attacks a different part of the mechanism, and it has a different effect on the Lineweaver-Burke plot. So just to show you what an uncompetitive inhibitor looks like, there it is in orange on top, and it's binding the ES complex. E is blue, enzyme is blue, substrate is pink. And what happens is the substrate binds, and that creates the binding pocket for the inhibitor. And when the inhibitor binds, it blocks the catalytic machinery. And so it basically freezes the enzyme into the enzyme substrate inhibitor bound complex. So this is showing what it actually looks like structure-wise. What does it look like on a Lineweaver-Burke plot? Well, it actually is pretty simple on this one. Here you have the y-intercept is changing, but the slope is not. So uncompetitive is simple in another way. You have the one thing of on the plot not changing, which is the slope, and you have the other thing changing, which is the intercept. Now, because the slope involves both the Km and the Vmax, but the intercept involves just the Vmax, you end up putting your alpha on the intercept part. But because Vmax is in both of them, it means that both the apparent Vmax is changing. The intercept's changing right here, right? And it's the 1 over Vmax. So it must be that the Vmax is changing, apparently, and both the Km and the Vmax are sort of changing the same way so that the slope remains unchanged. It's kind of like you have an alpha prime on both sides of the slope and it cancels out. Mathematically, it's not really worth it to understand entirely why it happens. It's easier to just remember. The other one had the slope changing and the intercept staying the same. This one has the intercept changing and the slope staying the same. And you can think about, if you understand how the Lineweaver-Burke equation works, it's pretty straightforward to say, oh, the alpha prime must be on the inhibitor, the intercept side of things. So if we could have E plus I on the left and E plus I in the middle, why can't we have both at the same time? Well, it turns out we can. All you have to have is you have to have the case where you can draw another set of arrows between the EI, like the substrate can bind both the enzyme, free enzyme, and the enzyme inhibitor complex. Basically, we're just saying if we can draw another set of arrows, maybe that can happen. And it turns out it can. This is called mixed inhibition because it literally is mixing, saying both of the previous cases go on. And we've got a bunch of arrows here. It's kind of ridiculous looking, but it's actually much simpler to look at on the graph, because instead of having a pivot point on the axis, we now have the pivot point between the x-axis and the y-axis in sort of the negative quadrant of it up there. So you have this pivot point, but you have the slope changing and you have the Vmax changing. It's just they're changing by different amounts each. So you say the one's changing by alpha, the other's changing by alpha prime, and then you can work out the math. It's way too complicated to show you how it works out, but trust us, you can work out the math for what the alpha, how the alpha relates to the Ki. Okay. Also notice over here, if 1 over Km is the x-axis way over here, the 1 over Km for this equation to work out, this axis will be changing by both alpha prime and alpha. There's some of this math is not stuff you'll have to get into, but if it makes sense to you, it's a nice way to look at it. So there's one other case. If we had a pivot point, we had a case of no pivot points. We had a case of pivot points on the y-axis. We had a case of pivot points between the y and x-axis. And there's a fourth case where the pivot point is on the x-axis. And therefore, the 1 over Km is not changing. That's actually a fourth kind called non-competitive inhibition. And that actually happens, but we're just basically saying this can show up, and it's just the logical fourth possibility if you have the pivot point on the x-axis. So this is how it all works, but the most common kind that you'll see is you'll see competitive inhibition where only the Km is changing and the Vmax is not, versus uncompetitive inhibition where they're both changing so that the slope remains unchanged, and then mixed inhibition where they're both changing so that there's a pivot point between the two axes. It turns out non-competitive is where alpha equals alpha prime, and that's why they cancel out to make the pivot point on the x-axis. But honestly, the most important thing is that you understand how those previous Lineweaver-Burke plots work, because you can look at it and just say, where's the pivot point? Is there a pivot point? Is the slope changing, or is the intercept changing, or both? And then from that, you can pretty quickly determine what kind of inhibition you have. Just to show you that it's real, this is non-competitive inhibition. It looks like this. It's a weird case where you have sort of the substrate binding here in pink, and the non-competitive inhibitor sort of binds off to the side. It changes the shape of things. It's weird, it's complicated, but the main thing about it is the pivot point, and you can see the pivot point way down here. Within error, the pivot point is coming together on the x-axis way down there in the corner. So that's the way I want you to think about it. Okay. You can tell these differences on a Lineweaver-Burke plot, and it's what Lineweaver-Burkes are good for. So there's one other thing about inhibitors is mostly we've been talking about inhibitors that form non-covalent bonds, but sometimes you can have a really powerful inhibitor that binds so tightly it actually forms a covalent bond with the substrate, with between the enzyme and the substrate. And so if that happens, and inhibition actually becomes irreversible on a biochemical time scale, I mean, you'd have to really pull hard on that covalent bond to get it off. And basically the enzyme is blocked permanently. These are called mechanism-based inhibitors because they look like the transition state. Now you've really totally blocked the enzyme. These are really valuable to drug companies because they know that it will be a good drug because the enzyme is completely blocked. This also gives you information about residues that are important to catalysis. If you have a residue that's doing nucleophilic attack, it's likely to form a covalent bond to an inhibitor. So if you throw a covalent inhibitor in, you can then do mass spec or something to figure out which enzyme residue is stuck to the inhibitor now. And that can tell you one of the important catalytic residues, and that's one of the ways that you can figure out what an important catalytic residue is. So for example, here's an example of a covalent inhibitor. So remember that we had chymotrypsin and we had the serine on it. And the serine forms a covalent bond. One of the reasons why we know that happens is because somebody used an inhibitor called DIFP. And what DIFP is, it's basically a phosphate with some carbons on it on the side, but the important thing is, look at that fluorine. It's a great leaving group. And what this does is this inhibits the enzyme and forms a covalent bond to serine 195. The fluorine leaves, and so this tells us two things. It tells us that the serine is a crucial residue, and it helped us figure out the mechanism that we showed you for the serine being the covalent nucleophilic attacking type residue. It also tells us that the transition state is arranged like a phosphate. And what's the shape of a phosphate? It's a tetrahedron. So chymotrypsin breaks an amide bond, which is a flat structure, right? But the way that it breaks it must be with the serine attacking and forming a tetrahedral complex, just like this tetrahedral complex down here. Because this works so well, we can deduce that the transition state is a tetrahedral state. And then that fits with how we're saying that the serine acts. If it's attacking the amide bond, the other three bonds get pushed back, and it makes perfect sense that it's a tetrahedron at that point. This is how we figure out what those mechanisms are. Here's another one. This is bromoacetal phosphate. So look at this one. And when you hear about a halogen like fluoride or bromine on a molecule, you immediately should think back to your organic chemistry days and think, good leaving group, possible covalent inhibitor. So look at this. This is an enzyme that binds this substrate, 3 carbons and a phosphate. Okay? 3 carbons and a phosphate and a bromine. If you use this, you competitively inhibit the triose phosphate isomerase, again, an important enzyme that's going to show up in Biochem 2. For right now, we're like, how do they know how this enzyme works? Well, they added this to it, the bromine leaves, and they find out that the substrate is now covalently bound to the inactivated enzyme at this glutamate. Therefore, the mechanism, when you talk about this in Biochem 2, you're going to see that it's a mechanism that involves glutamate. How do we know that? It's thanks to bromoacetal phosphate. So for these things, with covalent inhibitors, usually it's powerful, simple organic chemistry. Usually there's a halogen leaving group, because those are really good leaving groups, right? And those will form covalent bonds rather easily. Here's one more. Find the halogen here. Okay, so I'll give you a second to look at this. Iodoacetamide. What's the weird molecule? It probably stands out to you. The iodine, right? And so the iodine, if you add that to certain enzymes that run on cysteine, the iodine reacts with the cysteine, and then it forms a covalent bond, because that's one of the things that iodines will do. Thiols are powerful enough to make the iodine leave as a leaving group, and a covalent bond is left behind. There's a whole class of enzymes called cysteine proteases, and the way they found them is they threw iodoacetamide at them. They found out that it bound covalently to a certain cysteine, and then they knew that cysteine was important for some kind of nucleophilic attack. Very cool organic chemistry stuff. So covalent bonds are very important. It's actually a whole area in pharma news. So if you're interested in pharma, you should pay attention to this kind of thing, and you can apply your biochem and your organic chem to helping heal people. So for example, there's whole drug makers that focus on how can I make a drug that makes a covalent bond to what I know are the important residues in this enzyme. And this is a case where they throw this thing. Look at this molecule. It's got this little triangle. It's just a bizarre small molecule. But organic chemists designed this so that it would, number one, bind into the active site, and number two, react covalently with the lysine they knew was important in the binding site. Just by reasoning through this, they got a new drug, and this is actually voxelotor, which treats sickle cell disease. It's the covalent inhibitor, and I believe we showed it to you, didn't we? I could have showed it to you. I know that at least. And you can see its covalent bond. Look for the lysine. There's the lysine right there. So remember that lysine is a long chain with a single nitrogen at the end. Be able to find these. Like I promise, learning your amino acids is going to be worth it. It's going to be necessary to doing well in this class. And so actually irreversible catalysis or irreversible inhibition is actually a huge part of drugs. And so there's a famous protein chemist named Chris Walsh. And he basically talked about, he showed that these certain inhibitors were not just competitive. He's one of the ones who showed that this class of inhibitors formed covalent irreversible bonds. And in fact, he found one called D-cycloserine, which is shown over here. He actually isolated from Streptomyces. It was isolated in the 1950s, and Chris Walsh was able to, people said it was a competitive inhibitor, but Chris Walsh noticed the signs that it was not just competitive, but it was also irreversible. So it must be forming a covalent bond. They also tested it, it's safe, it's effective, and it turns out that D-cycloserine is called DCS, and it's used to inhibit pyruvate formation in a certain class of drugs. As you go through biochem, you might find covalent inhibitors, and these are powerful drugs. So you can look at these, and you can look at these Vmax and EM things. This is his data. This is from Christopher Walsh's own paper. And if you look at this, look at the Vmax. You have the irreversible competitor. So he tested the D version and the L version of the drug. And it turns out only the D version was irreversible. The other one was regular reversible competitive. And so he suggested that you use the D version of the drug. And it figured out not only a new drug that we can use, but it also told us how the enzyme works. Okay? So he also looked at other things about the numbers of this. The one thing that you can see over here on the left, on the right, sorry, you can see that the half time for inactivation was 4.5 minutes for this one, and it's 9.0 minutes for the other one. Okay, so this is one of the ways that we can give you test questions like this that are like that. So let's talk about the reading for test 2. They actually say that they demonstrated, in this study, we demonstrated that chloroquine and its analogs inhibited the main protease activity, which is essential in conserved enzyme in coronaviridae. I found this surprising because other evidence that I saw said that chloroquine did not work well against virus inhibition. So I wonder what was going on here. Their computer predicted that chloroquine and hydroxychloroquine would be potent inhibitors, and we talked about that evidence in the last lecture. So hence we cautiously concluded that chloroquine and hydroxychloroquine prevented SARS-CoV-2 infection by inhibition of the protease. Now actually, this was not supported, and so you want to look and see, okay, they say they have evidence for this. How strong is this evidence? They actually showed enzyme inhibition. And if you look at this, on the x-axis, look at the, this is a slightly different kind of plot. It's a straight line plot like Lineweaver-Burke, but look at the x-axis. It's actually a more straightforward x-axis. It's just inhibitor. They add more inhibitor, and then they do the 1 over V0 on the y-axis. So same y-axis as Lineweaver-Burke, but the inhibitor is going to be straightforward. You add more inhibitor, and what you see is as you add more inhibitor, and each line is a different concentration of substrate. So you have the different concentrations of substrate for the different line. If you have more substrate, it goes faster and the line is lower. Everything is making sense right now. But when you add chloroquine, you actually end up with it, hydroxychloroquine, it ends up going slower because it's inhibited more. And as you add more inhibitor, you actually end up going slower and it goes up in the graph. The main thing about this is it's a cool kind of graph called a Dixon plot. So see that the Dixon plot has a simpler x-axis. This is what a Dixon plot looks like for competitive inhibition. You have two lines at the two substrate concentrations, and from the intercept you get the Ki from that. So look at this, what they're doing is they're saying we got these two lines, and from the intercept we're getting the Ki. The Ki here is between 0 and -1. It's a negative intercept because it's clearly taking place on that side of the axis. Chloroquine, you're getting an intercept around -1 micromolar. So they're saying that we have a Ki that matches roughly, they're getting 1 from the plot and their computer predicted 0.5. They're getting 0.5 from the plot and the computer predicted 0.3. Okay, cool. But look at the error in these graphs and think about how they're drawing this line. How certain are you of where that intercept is? If you think about the way these lines look, it's fine, but it's not particularly strong or compelling evidence. If you imagine just a little wiggle in the lines, the inhibition might be at a totally different place, might not even be in the correct quadrant. So they're using this as evidence, and again, I'm not going to say it's wrong, but it doesn't force me to say it's right. Okay? You want to think about that. Just know that a Dixon plot has these two axes, and the intercept for competitive inhibition is going to be at the negative Ki. So they aren't trying to measure the mode of inhibition, they just assume it's competitive. That's another problem with it. If you look at the paper, you can see right here, experiments were performed, they calculated using a double reciprocal plot, and they don't say anything about how they know it's competitive, they just assume it's competitive. Now, the fact of the matter is it probably is, but this is another weakness to the whole thing. When you add up all these weaknesses, you end up with something where you're very skeptical that this actually shows that chloroquine works at all, much less how chloroquine works. So, remember that we say you should focus your reading on two important points. You have the drugs with the good Ki values, how they fit in the site, last lecture. The strength of the evidence for chloroquine and hydroxychloroquine, here it is. So look at this, maybe listen to it again. As you go through the lecture, think about the plot as you go through the paper, and we will discuss how it all works on that day. All right, so that is the first part of lecture 16. We've got one more little part. We've got actually 3 more videos, but they are going to be shorter than this.